Lesson 2 is kind of a review of what we did last year in geometry. None of the topics in this lesson are 100% new, so maybe we're just dusting off some old skills. But before we get to theoretical probability, wonder if anyone figured out why 0 factorial equals 1. So let's go and let's figure that out before we move on. So some of you may have seen this before if I did this last year for you, but I didn't do this for everyone, so I'll explain, and maybe you already knew why 0 factorial equals 1. But we need to figure out something first. 5 factorial. That is 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 3, 2, and then 1. So the question is why is 0 factorial equal to 1? Okay, let's figure it out. So this 5 factorial, 5 times 4 times 3 times 2 times 1, that's 120. 4 factorial, 4 times 3 times 2, that's 24. This is 6, this is 2, this is 1, and then we already know that this is 1 down here, but why? Well, what are we doing? How did I get from 120 to 24? Looks like we divided by something. We divided by 5. How did I go from 24 to 6? We divided by 4. 6 to 2, we divided by 3. Are you seeing what's happening? How do I get from 2 to 1? I divided by 2. So my pattern here is I'm dividing by 5, by 4, by 3, by 2. So that means I would have to divide by 1 in this last step. And 1 divided by 1 is 1. That's why, okay? Because what is this missing? This was missing the 5, this was missing the 4. Mathematics is not the study of numbers or the study of math or adding or multiplying. It's not so basic. Mathematics is the study of patterns. Mathematics is defined by patterns, and this pattern of dividing by 5, by 4, by 3, by 2, by 1, even though it's not intuitive, this is still the pattern, and that's what we are identifying. So there you go. Now you can put that mystery to rest, because I know it was keeping you up at night. I know you went home and you're like, man, why in the world is that? And you couldn't sleep. I get it. All right, theoretical probability. It's simply the probability of how likely something is to happen. It's sets of all outcomes called the sample space, and for equally likely outcomes, the theoretical probability of event, or written as the probability of event, is the ratio of the number of outcomes we want, favorable outcomes, to the total number possible. So let's talk about this as a coin flip right now. Theoretical probability. If I flip a coin twice, well, I flip a coin once, it's either heads or tails. It's only 2 options. That's my sample space, heads or tails. But theoretically, if I flip it twice, in a perfect world, one would be head and one would be tail. The probability of how likely something is, it's 50-50. Okay, half the time it's going to be heads, half the time it's going to be tails. For likely outcomes, let's say I flip a coin and I want it to be heads. Well, the number of outcomes that I want favorable, I only want heads. That's 1 outcome out of total number of outcomes, 2. 1 to 2. That's a ratio, but it also can be written as a fraction. 1 over 2. That's 50%. So at a really basic understanding, that's what theoretical probability is. Okay. All right, sample space of events with simple events. A jar contains 32 red marbles and 28 blue. What's the probability a randomly selected marble is red? All right, well, let's figure out our denominator. Let's figure out the total amount of marbles in this bag. 32 and 28 make 60. Of those 60, how many are the ones that we want? We wanted the red. That's my probability, 32 out of 60 marbles. And then reduce if you can. Always reduce the farthest you can go. I accept percentages on this. Well, I'm guessing Gamble is gonna accept percentages on this, but fractions are totally fine too. A letter in the word restoration is randomly picked. It's the chance it's a vowel. Well, how many different letters do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Of those 11, how many are vowels? 1, 2, 3, 4, 5. And I can't reduce that anymore. 2 die are rolled. 2 dice, 2 die. What is the probability that the sum of the 2 dice in the next roll is at least 9? Okay, so that's a little tricky. To understand that, we need to build a better sample space. We need to figure out, how did this do it? Yeah, okay. All right. Okay, no way to do it but to do it. You did this earlier in the year when I was gone. I had you build a table for me. And then we rolled some die, and we said, okay, your first die was, the outcome was 1, 2, 3, 4, 5, 6. Those were the chances of the first die, like those are the outcomes. On the second die, same deal. 1, 2, 3, 4, 5, 6. Okay, so I have a red die and I have a blue die. So now let's figure out the sum. 1 and 1, if I roll a 1 and 1, my sum is 2. If I roll a 1 and then a 2, my sum is 3. And we can go and we can build and we can fill out this chart. And that is the whole thing. All right, to answer this question, what is the probability that the next roll, the sum, is at least 9? We need to figure out our denominator. How many total outcomes are possible here? You can count these boxes. You have 6 in a row, 6 in a column, 36. Now let's figure out how many of these are at least 9. Remember, at least 9 includes 9. So those ones, 10 is at least 9, 11, 12. How many of these outcomes do we like? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of 36 is the probability. Reduce if you can to 5 over 18. So the probability that you roll 2 die and you get at least 9, 5 out of 18 times. A day in the month of January is randomly picked. What's the probability of selecting a prime number? Okay, so prime numbers, we gotta list them. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. And January has 31 days. So 31 is also prime. Okay. There are 31 days in January. That is the total number of days. So total outcomes possible. How many of those are prime? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I cannot reduce that anymore. What's the probability of drawing a heart or a club from a standard deck of cards? Okay, so over here, this paper right here shows the breakdown of all of the sample space of a deck of cards. There are 4 different, what do you call them? Oh, I can't think of it. The different categories, like the diamonds, the hearts, I can't think of the word. It's gonna bug me. I'm not gonna stop recording, I'm not gonna look it up. Someone knows and they're probably screaming at, they're like, Kilburn, you're an idiot. Well, where were you right now? Probably in another class. That doesn't help me. Anyway, there are 4 different types. I got hearts or a club. There's 52 cards in a deck. And since there are 4 different, oh come on, suits, that's what they're called. It's written there, suits. There are 4 different suits in a deck. I want a heart or a club. Well, there's 13 hearts and there's 13 clubs, which means 26 out of the 52 cards in my deck are good for me. Okay, the probability of getting that equals a half. Half of the time you pick a random card, it's going to be a heart or a club. Suits, guys, it's called suits. 8 books lettered 8H on a shelf. If Scott randomly picks 2, what's the probability he chooses books A and then B? Okay, so he just wants A and B. All right, let's see. I see the word choose. 8 books, choose 2. 8, choose 2. 28. Okay, choose. Okay, complement event. The complement of an event is the probability an event will not happen. Since the sum of all probabilities in sample space is 1, okay, it's 1 because think about that coin again. Half of the time it's heads, half of the time it's tails. 1/2 plus 1/2 equals 1. Or rolling a die, it's either 1, 2, 3, 4, 5, or 6. 1 out of 6 is a 1. 1 out of 6 is 2. 1 out of 6 is 3, okay? 1 plus 1, all the 6s together gives you 6 6s for 1. The probability of a event, the complement is not happening, is 1 minus the probability of the event. Now that's a complicated way to say if, okay, let's give it, I don't know. Let's just jump into examples and see if it makes sense with examples, because everything always makes more sense once you start doing a problem based on it. The probability that it will snow tomorrow is 7/20, 35%. What's the probability that it won't snow? Okay, well that's going to be 1 minus 7/20. And you can do your calculator, you can do that, you can hit math, enter, enter, but 1, if I want it to be 20, that's going to be 20 out of 20. That's going to make 1. Gives you 13 out of 20, which is also 65%. So you also could have looked at this and you could have said, okay, well 7 out of 20 like I did, and I'm like, I just know that's 35%. You could have said 1 minus 35%. Well, 1 in percent is 100. So 100% minus 35% equals 65. And those are equivalent things. Month of the year is randomly picked. What's the probability of getting a month that does not begin with the letter A? So how many letters begin with A? I think I have April, August, and I think that's it. Yeah. Okay. So I have 1 minus 2 out of 12 months. It's going to be 12 over 12 minus 2 over 12. 10 over 12, reduce that to 5 over 6. Okay. So if I randomly pick a letter that does not begin with A 5 out of 6 times, that makes sense because most of the letters don't begin with A. So most of the time, I'm going to not get an A. The spinner to the left is spun. Find the probability it lands on a number that is not prime. Okay, so we need to figure out, first off, how many samples are here, 16. So I'm gonna say 16 out of 16, that's gonna represent my 1 in this equation. Number that is not prime. Find the probability it lands on a number that's not prime. Okay, well let's figure out the prime numbers. Two, 3, 5, 7, 11, 13, and that's it. 1, 2, 3, 4, 5, 6. 6 out of 16. So that gives me 10 options that are not prime. So 5 out of 8 is going to be not prime. 2 dice are rolled. What's the probability of not getting doubles? Okay, so I made this chart up here before. I'm going to come back to it. there are still 36, that's really big. There are still 36 possibilities in the sample space. How many doubles do we see? Well, what is a double? It's a 1 and a 1. 1 and 1 make 2. 2 and 2 make 4. 3 and 3 for 6. 4 and 4. 5 and 5. 6 and 6. So I have 6 double chances. 1, 2, 3, 4, 5, 6 out of the total 36. So not very many ways to make doubles. There are 36 over 36 different outcomes. That represents the 1. We're going to take away the doubles. 6 out of 36 gives you 30 out of 36, and we're back to 5 over 6. What's the probability of not getting doubles? Again, pretty high. If you roll die, you do not expect to get doubles that often. The complement of an event, the chances that it will not happen. Okay. Now we're talking about compound events. Oh, did not have this. Huh. I'm missing a page. Compound events, the probability of 2 or more simple events when the outcome of an event does not have an effect. I'm coming back for those formulas. I don't remember. I don't really use the formulas super much. Independent events. Well, oh yeah, actually I know this one. No, I don't know that one. I lied to you. I don't know that. The die is rolled 3 times. What's the probability of getting 1s on each roll? Oh, that bugs me. I don't have that page. Independent events. All right, so I roll a die. What's the probability of getting a 1 on each roll? Well, take it 1 die at a time. It doesn't matter what I roll for the first die. It's not going to affect my chance of getting the same thing on the second one. So 1 out of 6 times, I'm going to get a 1 for my first die. And then I'm going to need to roll again the second die. And I still have 1 out of 6 odds to get that 1. And then for the third die, it's still 1 out of 6. The rolls don't impact each other. I have the same likelihood of getting a 1 every time. 1 over 216. So only 1 out of about 200 times am I going to get 1s 3 times in a roll. Not very likely. A coin is tossed and then a day of the week is selected. What's the probability of getting tails and then getting a day that starts with T? Okay. So if I flip a coin and I get tails, the chances are 1 out of 2. What is the probability of getting tails and then a day that starts with T? There's only 2 days in the week that start with T, Tuesday and Thursday. 2 out of 7 days. 2 out of 14. 1 7. Compound events need to be multiplied. They are and statements. I need the first to be a 1, the second to be a 1, and the third to be a 1. It needed to be heads, and I needed a day that started with T. When things depend on each other, when events depend on each other, you have to multiply those probabilities. I'll probably come back for those in the next video. Okay, a bag contains 8 red, some crayons, and some purples, and there's yellows, and there's greens. A crayon is selected, put back, it's replaced, and then another is selected. Find each probability. Okay, purple and then yellow. Okay. Well, how many are in my sample space to begin with? 8 red crayons, 14 purple crayons, 6 yellow, 4 green. Looks like there's 32 crayons total. All right. Let's see, a crayon is selected. What is the probability of purple crayon being full? Well, that's 14. 14. And then if I put that crayon back in the bag, I still have 32 crayons to pick from for my second pull. The chances, the next one is yellow. Well, there's how many yellows? 6. Okay. Man, not having the answers in front of me is a bummer because now I gotta go get a calculator because I can't do this math in my head. good, but I'm not that good. Also not good enough to just have compound whatever formulas memorized from a year ago, but that's on me. All right, let's multiply the numerators. 14 times 6, 84. 32 times 32, 10, 24. And let's reduce that. 84 divide 10, 24. We're gonna hit math, enter, enter. And we're gonna get the smallest form of that fraction, which is 21 over 256. So not very likely. That's about, it's less than 10%. It's like 8%. So not very likely. Red then green. So green then red. All right, green. How many greens we got? 4. I got 4 green. And then red. 8. Okay. So that one, substantially more likely, maybe. I don't know. No, that's actually wrong. That's like 3%. It's way low. Just because the number's smaller, I thought it was better odds. It's not. It's not better odds. Okay, 2 purples, a purple and a purple. Well, there's 14 purples. And remember, I'm pulling that crayon out and then I'm pulling it right back in. So I still have 14 shots. And 196 divided by 1024, math, enter, enter. 49. Added 256. Okay. And then 2 yellows. 6 out of 32. And then I put it back, so there's still 6 out of 32. 36 divided by 10, 24. Math, enter, enter. 9. Okay. All right. Now, independent events don't affect each other. Okay, the first pull of the bag, as long as I put that crayon back, does not affect the second pull of the bag. But dependent events are completely different, obviously, independent versus dependent. Using the same sample space from above, assume that once a crayon is selected, it is not replaced. I took that crayon, I pulled it, and I chucked it across the room. It's no longer in the bag anymore. So the second event is going to be different because of the impact of the first one. So let's write down what happened. I had 8 red, 14 purple, I think. I think there were 6 yellow. Is that true? 6 yellow, 4 green. Okay, all right. The probability I pick a yellow crayon is still the same. There's 6 out of 32 options. But now I pulled that yellow crayon out. I'm assuming I did that. I'm assuming I hit this. I'm gonna take that crayon, I'm gonna chuck it across the room. Now there's no longer 32 crayons in the bag. There's only 31. Then red, there are 8. Okay, so 48 over, now I don't remember what that is, 32 times 31, 992. Reduce that if you can. 3 out of 62. Purple then green. All right, well there's 14 purple out of 32 choices. Again, I'm taking a purple out. I'm not putting it back in the bag. It's going somewhere. It's probably going across the room. Means there's 31 left in this bag. There are 4 green. 56 out of 992. 7 out of 124. 2 reds. Okay, there's 8 reds. 8 out of 32. Now, if I take that red and I throw it across the room, right, I got 31 crayons in this bag. But I don't have 8 reds again. I got one of them. One of them already accounted for and it's gone. Now there's only 7 reds left in the bag. and that's the same thing. I don't know why, I just did that. Some of you might be making fun of me. Whatever, kids making fun of me, you can do 20 by yourself. A card is drawn from a standard deck, not put back, not replaced, and another is drawn. What's the probability of choosing a heart and then a spade? Okay. There are 52 cards in a deck. Of those 52, 13 are hearts. Okay, if you don't know that, right here. Also play with cards. Come on, guys. I know it's 2025 and you're all on your phones and your tiki-takis, but like, can we understand that there's, you know, cards, kings, queens, jacks, people know what they are. There's 4 of each of them. You know, common things like that is just gone. We're just yelling to an empty room about modern society. I'm old now. I'm officially old. All right, 13 out of 52 hearts. Now, I'm pulling one and I'm assuming that I got it, and it's not replaced. So that means that the card is gone. There's 51 left in the deck. Spade. There are still 13 spades, because again, I'm assuming that I got the heart the first time. So this is gonna be 169 over some large number. 2, 6, 5, 2. Okay, reduce if we can. I'm not sure. I'm guessing that you can, though. Okay, yeah, 13 over 204. Jack has 4 Snickers, 8 Mars. He randomly chooses a piece of candy. He eats it. Savage. And then chooses another. What's the probability of both candy bars for Snickers? All right, well, he had 12 candy bars, right? 8 Mars and 4 Snickers. Okay. Pet peeve. Pet peeve. Either commit to spelling the word out or put the number. Okay, none of this like 4, 8, pet peeve. Also, it's a math class. Can you put the numbers? Okay, just easy for me to like look at that. I don't want to find the number again. Whatever. Anyway, there were 12 candy bars. Probably they were both Snickers. He had 4 Snickers at the beginning, and then he ate one. There's only 11 candy bars left. He's not puking it back up and putting it in the bag. I mean, maybe he is. Jack is a weirdo. He spells and then writes numbers. Okay, Jack is a sociopath. But assuming that he didn't regurgitate his candy, we are going to have 3 Snicker bars left. 3 of 11. That's going to reduce to 12 over 132, which is 1 out of 11. All right. That's it. Stay tuned for the actual formulas. I'll find them. I'll put them there. But really just know, okay? Just know that compound events depend on each other. Okay? You need to multiply to make it happen. Let me give a small example of my life from, okay, that some of you might be able to identify with. I guess I can't zoom in super far. Not that I would like, anyway, for compound events. Some of you might also remember this story if you had me last year when we talked about this unit. So compound events depend on each other. That means they're multiplying. Okay, so let's talk about Pokemans. Pokemans is a secret amount of math that just hides behind it. You don't get to see it. You don't appreciate it necessarily as a casual player of the game. But if you're getting into competitive nitty-gritty, there's a lot of math in Pokemans. Now let's imagine, okay, I am a Pikachu's. And you know it's a Pikachu because it's going Pika, Pika. Okay, that's what it's saying. All right, Pokemans, they say their name. Okay, it's like if I walked around going, Kilborn, Kilborn, Kilborn. Okay, Pika, Pika. All right, and I was a young kid. This is a true example. I was having my Pika Pikas over here, and this is a Zubat. It's not good, but you know it's a Zubat because it's saying Zubat. It's the worst bat I've ever made. Whatever. They're fighting each other. I'm playing a little game on my Game Boy, and they're fighting each other. Okay, and let's just say for this example, that Zubat was being the most evil Zubat in the world, and it has confused me, which is a thing. In Pokemon, it's a status, you can be confused. Okay, Let's say that also it did a move that paralyzed me. Okay, that sucks, but it happens. I don't know if that's a Z. Is there supposed to be a Z in that? Yeah, okay. That looks better. Okay, paralyzed. And Zubat is particularly annoying because they also know a move called Bite. And what Bite can do, some of you might know, is it can flinch you. Okay, so here's an example, and they're fighting. This guy's trying to go like lightning. He's going trying to shoot lightning, you know, like the Force at the Zubat. That's what I would like to happen, but that's not what actually happened. So here I am, like literally me. I'm playing with my Game Boy Advance many, it feels like 1,000 years ago, okay? And I have a Pikachu who has all these conditions happening at the same time, and I'm just trying to kill this stupid Zubat. All right, so what happens when you're confused? One half of the time, you don't attack. You hurt yourself. It's just how it works. Your attack doesn't go through. Okay, so, but if I clear this one half, I got the good half that lets me attack. Now I need to do the paralyzed check. 1 out of every 4 moves, if you're paralyzed, will not go through. Okay, so I need to clear, I need to get this good half that lets me go through. And then I need to beat, okay, the paralysis of 1/4. Let's call it 3 out of 4 because that's the complement, right? That's the chance I get to attack, only 3 out of 4 times. And then flinching, okay, well, you would flinch, I don't remember the exact proportion, but I believe it's something like 1/3 of the time. So that means 2 out of 3 times you will continue your attack, okay? So 1/2 not attack, 1/4 not attack, and then 1/3 not attack. Well, how this relates to compound events is these events depend on each other. I need to clear this boundary before I move on to that one. I need to clear that one before I move on to this one. I need to see if I do this one before I can actually shoot my Force Lightning at the evil Zubat. Okay? Well, let's figure out the probability of all of this happening, the probability that I clear all of these barriers. They would need to be multiplied by each other. So 1 times 3 times 2 gives me 6 for my numerator, and 2 times 3 times 4 gives me, what is that, 12? Brain power, 8? No, 8 times 3, 24. Okay, yeah. So the chance I actually get to attack is really low, 1 out of 4, or 25% of the time. Okay, so here's where young Mr. Kilborn got very mad at math. He was in the cave, he was trying to shoot the thing, but like either I wouldn't clear this 50-50 and I'd hurt myself, or I would and the game would say you can't move because you're paralyzed. And then what ultimately made me rage is when like I got these two because it said you flinched. That means I had beaten this one, I'd beaten this one, and I lost on this chance. All of this together, I only had 25. So little me trying to fight the Zubat, can't attack after can't attack after can't do it because 75% of the time I'm doing nothing. And then eventually I got real mad and I think I punched my Game Boy, which is not something that I recommend or ever, you know, like no one should get that mad about a video game, but I've seen what you guys rage about, so like at least some of you can relate to me. I literally punched my Game Boy and I broke the screen, and I was really scared because it was expensive. It was like a $200 Game Boy, and I just punched it because of the Zubat. So what I did was I lied. Okay, I lied. This is a bad example of a story, but I lied to my dad and I said that I stepped on it. I said that I put it on the floor and I got out of bed and I stepped on it. Also irresponsible, but less bad than I punched it. So I lied that I stepped on it and he got me a replacement one. I think if I told him that I actually punched my Game Boy, there's no chance I was getting another one, but it was an accident that I stepped on it. Okay, moral of story, first and foremost, math. Okay, math is in Pokemans, and it's more prevalent than you think. Second moral of the story, don't rage so hard that you attack your electronics, children. And then third, please don't lie to your parents, even though I just told you an example of a story where it benefited me that I lied. Don't, okay, don't. And yeah, there you go. This one went a little weird. I still gotta get those formulas for the other thing. But just know that compound events depend on each other with multiplication.